Welcome everybody to Berlin. Isn't it nice? 10 years of C++, and I decided I'm not like the German train system. We start on schedule, right? So welcome to Berlin. Welcome to Meeting C++. I hope you enjoyed it. There were plenty of great keynotes. There is one closing keynote by Peter Sommerlath, so make sure to watch that one as well. You will definitely enjoy it. The topic of my talk is fast and small C++ when efficiency matters. And it's a nice topic because you can talk to everybody because everybody has a different understanding. So it's really great. I worked a lot in embedded systems, embedded development, tiny devices, not only physical scale, but also on the software level, so 512K ROM, 128 RAM sometimes. And I and the others had to squeeze in a lot of functionality into that device, and there were others similar scale. So I like this, trying to squeeze a lot of features into small space. And the question then often comes, or the decision we have to make is, make it fast or make it small? Usually, the two do not go that well together. We have to make a decision. I'm Andreas Fertig. I'm available for C++ training or consulting services worldwide, remote or on-site, whatever is best for you. We make it work. I'm also the author of a couple of books. Jens was so kind to put my latest one up there, Move Semantics. And I'm the author of a tool called C++ Insights. And in one or two places, we might see the tool coming up. Okay. So what I'm going to present are a couple of techniques from the standard library, how they do things there. I have a section in that I learned from a real-world experience with a customer. And there's one nice thing at the end where you don't have to do that much. So this is the usual slide. And this is a very special presentation, very special talk, because usually I'm abroad for giving talks and not in my home country, Germany. Since we are all here, I suspect that a couple of you more than usual are speaking German or at least understand a bit of German. So for those who aren't and watching the talk potentially later online, my last name is Fertig. It's a very typical German word, not necessarily a very typical German name. But it's an adjective in German, and you can translate it to finished, ready, complete, or completed. So it's a very nice meaning. It's a little context dependent what you really mean. So is your project ready or is your project finished? The one could imply that you're ready to start. The other implies that you're already finished it. And so you can play a lot of tricks with the name. The bad part is, since it's an adjective, it's spelled with a lower first letter in German, in the regular sense. And the spell checker, of course, knows that. But it has a tough time to fight with it when it's used as my last name, because then it's a capital first letter. And Andreas Fertig would form a okay sentence in C++ without Fertig being the last name, right? So interesting things, it's a little ambiguous, reminds me of the language we are here today, right? We can express different things in different ways. So let's dive into C++ because I think I'm not the best German teacher. This is a piece of code I hope and I guess that most of you have written and used it. It's a unique pointer, right? And the usual usage of a unique pointer is we tell that unique pointer the type it should maintain. So the type T, usually instar or your own class type, that is maintained by this unique pointer. It's the dynamic memory this unique pointer holds. What I'm showing you here is a less frequently used version, at least in my experience. A unique pointer in reality can take two parameters. The first one is the one I already spoke about that we all know. The second one is a little less known. It's the deleter function. And by default, the deleter that kicks in says delete. Easy. But we can teach a unique pointer to do things differently, to work with a thing that wasn't allocated with new and hence cannot be deallocated with delete. So my regular example is here going to POSIX fopen, which returns me a file object, which badly for talks is the structure file. So we get something back that's called a file. This is the type that my fopen allocates. Whether it does this with new or with some other technique, it's out of our reach. But it returns me something that later has to be destroyed. And we say we close the file. Destroying would be bad, potentially. So we want to close it. And we now can teach this unique pointer to say, well, since you haven't said new, we didn't use make unique, you cannot say delete. And instead of delete, please call fclose. And what you see on this slide here in line number 2 is that after the type file, which is the pointer type inside the unique pointer, we teach that unique pointer the function signature of fclose. And since I always forget whether it returns void or int, I use decal type on fclose here. This is my deleter. And since I have passed in a function pointer essentially as the deleter, I have to teach the unique pointer with a second parameter in the constructor, the address of fclose. Okay, are you all with me? So that works splendidly. It's perfect. Unless if we start talking about efficiency. I mean, the address of fclose, it's known at compile time, and if you like to defer the decision a little, let's say link time. But the binary knows where to find fclose. Usually our unique pointer stores a single pointer. So if you query with size of the size of a unique pointer, it returns you the size of a single pointer. With the custom deleter technique here, if I query the size with the static assert, you can all see, assuming that this code really compiles, that the size of my unique pointer variable f here is larger than the size of a void star. So it stores more than a single pointer. Effectively, unless we are really talking about function pointers sometimes, you can say it stores the size of 2 pointers. So you just increase the size of your unique pointer by another pointer, so 100% more. That's not necessarily a good thing. Because, as I said, the address of fclose, it's known. So why have storage space for it allocated and the indirection querying another pointer to get that address? Sounds unreasonable, right? We can do better. The unique pointer can do better. And this is the trick here. What the standard library here does, and we will peek into the unique pointer implementation, is it basically uses an optimization technique that's there for a long time, and it's called EBO. It stands for Empty Base Class Optimization. And this is a special optimization the compiler can apply in the specific case that we have a base class that comes with no non-static data member. So no member variable that's not marked with static. Statics would be fine. They do not contribute to the size of the class anyway. So a class without any data members that are not static. That class has the size of, well, it depends. If you don't ask, it has the size of 0. Once you start asking about the size of this base class here, the compiler returns you 1. Because in C and C++, everything needs to be addressable. And to get an address to something, it needs at least to be the size of 1. So even your empty classes, if you query them with size of, compilers usually will tell you 1. EBO now says, well, but if you have this empty base class, which can have member functions, and you derive from that one the combination of the base class and the derived class only occupy the storage space required for the derived class. So I try to make it very easy for you here. My derived class has a int 32t, so it's a fixed size type. Platform doesn't matter, so that means 4 bytes, right? My base class is empty, derived here derives from base, and if I static assert on the 2 size-offs from d and from int32t, we can see the derived object d has a size equivalent to an int32t. So the base class does not occupy any storage space. And this is the base of the trick, because my base class can have functions, member functions. It just does not have, or it must not contain any data. So the first thing is the standard library in the unique pointer has something called a deleter. What it does is deleting something. So my default delete function here, or class type, it's a class template. It takes a single t, and it comes with a call operator taking a t star, and internally it calls delete on that pointer. So this is the thing that runs by default if you pass only one template parameter to your unique pointer. Okay? But that class here is empty in the sense of non-static member functions. So that constitutes for EBO. Now, the implementation of a unique pointer, a reduced one, of course, but that does the job here. Looks like this. We have our class template unique pointer taking 2 template parameters, at, as we all know it, and the second one, I call that one del, and it's defaulted to default delete of t. So the object I just showed you, the class type, this is used as a default parameter. So this is why we don't have to pass a second parameter. And now internally, my unique pointer stores a compressed pair. And we will look in a minute what compressed pair means, but it's basically storing 2 things. Pointer to the data and potentially a pointer to the deleter, right? I have a constructor, of course, taking a single argument for my unique pointer here in B. I have one with 2 arguments. The first one constructs my pair with a single argument. The second one, the pair with 2 arguments. You know the drill, a unique pointer, it's not copyable, it's only movable, so the copy operations are deleted. The move operations are implemented here, and if you go down to D, you can see in the destructor, you have a little, maybe odd-looking code. The reason for that is that compressed pair in the standard library is used in a lot of places, not only in a unique pointer. So they usually go with the notation saying first and second and not naming it deleter or something, which would be more meaningful. So in the unique pointers deleter, what they are doing is they checking the second member of the compressed pair. Looks like a pointer, right? So if that's not a null pointer, then obviously we have data there, which we must delete. And then we invoke mPair first with mPair second. So we invoke a potential function stored in mPairs first with the pointer stored in mPair second. As I said, you could make that better, but this is a utility class mPair compressed pair that's used in more places than just a unique pointer. So this is how a unique pointer looks. So it does never store in this implementation 2 pointers at no time. And also we do not have different implementations for single or 2 arguments. And I had a decision to make at this point, and I thought, well, do I want to scare away people or not? And I went for not. This is the C++20 version of a compressed pair. The C++17 and previous version would not fit on a slide, because to use EBO, as I showed it to you in the beginning, you have to start using inheritance. And then things get messy. So C++20 helped us clean that up with the attribute no unique address. No unique address implies the same thing as an empty base class. It basically says if the class or the object we are attaching the no unique address to does not come with any non-static data members, it can be 0 in size. So see it maybe as a union that we have here, but both of them can be active at the same time if that helps. But they can have the same starting address. So first and second here can technically have the same starting address. They do not occupy storage space if they are empty. So my compressed pair here takes as a first type my deleter, and as a second the T that my unique pointer was typed with. And I say they are both of type unique address. So first is my deleter, second is my T. And I have two constructors here, one for the one argument case and the other one for the two argument case. Now, this allows me technically to say, okay, if I have a deleter that follows the rules of the default delete that I showed you previously, then del here would have a size of 0, and my entire compressed pair would only have the size of a single pointer. And thanks to that, if you sprinkle in a bit more C++20, you can do it without, but it's the nicest version. I can form some helper utility somewhere in the code base where I combine a couple of things from the latest C++ standards, where I say, okay, I have a using alias being a template. That one takes a type name T, and as a second parameter, C++17 auto parameter. So that's a non-type template parameter where I'm not saying what exactly it has to be. Let the compiler deduce it. My using alias points to a unique pointer. Std unique pointer, it says it's typed with T. And the second parameter, my deleter, here I'm using C++20. I'm using decal type on a captureless lambda because in C++20 we can have captureless lambdas in unevaluated context and deduce their type. And this is what I'm doing here. My captureless lambda takes a T star as parameter and it invokes that parameter objt, or it invokes delete fn with that parameter objt. So whatever delete fn is, we are passing objt to it. And as you can see in line number 5 now, I can use this unique pointer deleter, as I called it, say it's of type file, and say the thing that you should call when destroy is appropriate, it's fclose. And since fclose now is by that entire machinery deduced as a function pointer, which is wrapped in my lambda, and my lambda is a class type with no non-static data member, so it qualifies for EBO. So the lambda itself, if you query it, as I said, if you query it, it has the size of 1, but technically it has the size of 0. But it knows with its call operator which function to call, and that one is known at, as I said, how you want to phrase it, let's say link time. So the size of my unique pointer deleter here is equivalent to the size of a single pointer. So I just saved storage space. I just saved time because I don't have a hop on indirections. And the API is more beautiful in my book, at least for my users, because to construct this unique pointer, you have to do the same thing as always and not to pass in a second parameter to the constructor, which you can confuse with the actual parameter and it might compile but invoke the wrong function. So this is compressed pair from the standard library and doing things efficiently there. The standard library also comes with a type that we very often use. That's a std string, right? But before we go to the std string, you can write this code for compressed pair even a tiny bit better. With C++23, you can have a static lambda. And that means your lambda comes with a call operator that's static. It's a static member function. And what's the difference between a non-static and a static member function? The first implicit dis parameter. Static member functions do not have that implicit dis parameter. And that means your function signature just has one parameter less, but mainly in the background it means the compiler does not have to create you a pointer and pass it and nobody cares about it, because inside a lambda the dis pointer is not required. It's a captureless lambda, so no member functions, no non-static data members. And by making that thing static, you can squeeze out around 1 to 3 additional assembly instructions that were used before and now are no longer needed. And the compiler will most likely not be able to optimize this away without making your lambdas call operator static. For the full picture, you can also make the array index operator in C++23 static as the call operator. So it does not belong only to lambdas, but this is a nice application area here. Now the next thing, as I said, what we often use in the standard library is a std string, right? So how does a std string work if we think about that? Some time ago, a long time ago, we decided, well, a std string stores a pointer to the string, obviously. It has to keep track about how many characters are stored in the string, and it has to keep track about how much dynamic memory was allocated. So these are the 3 things. And since it uses dynamic memory allocations, we then also said, well, do we really want to start allocating dynamic memory for just 1 character, for 2, for 3, for 4? So is there a threshold when we can say it doesn't really make sense to reach to the heap? And so roughly we can say less than 16 bytes, that might not be worth it. So this is why std string comes with a small string optimization called SSO. The small string optimization says, well, if you store less than a certain amount of characters in your string, your std string comes with a fixed sized array in itself. So that resists on the stack and not reaching to the heap. And everything that's below the threshold, usually around 16 bytes, that's put in this array, and once you exceed with your std string that length, it goes to the heap and everything is stored in the heap. Okay, so that's SSO. If you think about that and put it into code, we can say, well, such a string struct or class here, it has to store a size, let's call it m size, we give it size t. We have to store something that's the capacity, let's call that one type size t as well. We have to store the car pointer, let's call that one mdata, and then we have obviously to store the SSO buffer somewhere, so in the string, so a car array of, let's say 16, call that one mSSO buffer. And now I created 2 modes in my std string. The long string mode going for the heap and the small string mode using the stack. So we need some way to store in which mode we are. So let's add a Boolean to that and say it's m is SSO and that one is by default true. If we are summing that one up on a 64-bit architecture, we are getting 48 bytes out of that thing. 48 bytes just because we wanted to store 16 bytes. We had to add a Boolean, and we got a lot of padding bytes. So if you start using C++ Insights, C++ Insights comes with a transformation that says show padding information. And if I do the transformation here, then we can see C++ Insights tells us, aside from the offsets and everything, that we have 7 bytes of padding in the structure. So we added 16 bytes to optimize for a case, and now we wasted 7 more bytes. Obviously, we can optimize that. We could increase the small string buffer. But what is it that your standard libraries do, right? And now I like to share what the 3 major standard libraries do. So that's lib C++ shipping with GCC, that's lib C++ shipping with Clang, and MS3C unnamed standard library, so let's call it MS-STL. We make another change. We say to compare them, they all should have the same total size, 24 bytes. This is not a reality. In reality, they can be more flexible. So we are want to be able to compare them in a fair way, so 24 bytes in total. We want to go down away from this 48 bytes. The first thing here is loop stood C++, so that's what GCC ships with. And what they're doing is they say, well, we obviously have to store this char star and pointer. That's fine. We have to store the size, so how many characters are currently in that string. But then we can do better. We can say, well, we use a union. And that union contains the capacity or my small string buffer, in this case of 8 chars, because we wanted to fit everything in 24 bytes. This union is based on the assumption that we either need the capacity, because we only need the capacity if we are reaching for dynamic memory. Then we don't know how much memory we have, so we have to store it somewhere. For the small string buffer mode, we know it's 8 characters, because this is the size of my buffer. So we don't know the capacity information necessarily. And this is the trick they are doing. They say, at the time, we only need one of the two informations. Either we need the capacity because we are in long string mode, or we're in small string mode, then we need the buffer. So this is why they are neatly aligned to each other to the size of a size t. Now, the static assert here proves that if you sum everything up, it's 24 bytes, right? And here now come a couple of helper functions that might or might not be there in reality. As I said, it's a downtrimmed implementation. We have max capacity to compare the things. So the max capacity that this stood string implementation can store is the maximum of a size t. We have SSO capacity. SSO cap here is the size of mbuff minus 1, because we are backwards compatible to C, and while my stood string knows how many characters are stored in there, we have this C SGR function, and that has to be null terminated. So from this entire SSO buffer, we have to subtract 1 character for the null terminator, because every string here must be null terminated. Means 7 bytes of payload in this implementation. A helper function fits into SSO. Well, it simply checks whether the length is sufficient for the small string buffer or not. And then we have the function isLong. And that one's the crucial function, because that one figures out whether we are in long or in short string mode. And isLong here says, if the address of mPointer is not equal to mbuff, we are in long mode. So this is the trick they are doing. This is how they abstracted the Boolean away. Then we have a constructor taking no arguments, default constructing a small string object, and we have the constructor taking 2 arguments, a string and the size, or const star and the size, and their mPointer is initialized with mbuff if the string fits into SSO. So we let a pointer point to our stack space, and otherwise we allocate memory on the heap and let mPointer point to that. So in the constructor's body, one thing we have to take care of now is to say if we are in long mode, then we have to set a capacity to the length that we just allocated. And of course, at some point, we should copy the data over unless we don't want to store them really in that string. Size and data are easy. They directly fetch the members, so msize and mPointer. In capacity, we get a branch now, because there is a check. If we are in long mode, then we return mCapacity. If we are in short mode, we return SSO capacity. So here you're paying with a branch. Okay. This is lib stood C++. How does Microsoft do things? Slightly different, but similar. Microsoft says, let's start with a union. We can't do things like the other people did, right? So the union here stores a char pointer and my small string buffer of size 8. So they playing things differently. And after that union, where the pointer and the buffer are next to each other, we have msize and mCapacity, both of size t. The sum of all of them is once again 24 bytes. Max SSO or max cap is still the size of a size t. Max SSO cap is size of mbuff -1, so 7 bytes payload, effectively. Fits into SSO, same thing as before. Islong now has obviously to do something different. Islong says if the capacity exceeds the small string capacity, we are in long mode. And if not, we are in short string mode. So they are storing that flag in the capacity information. And they do this because if you look down, what they do in size and data is for size, they return size, for capacity, they return capacity, but for data, they now have the branch there. They check if we are in long mode, then we return the pointer, and if we are in short string mode, then we return the buffer. So they made that decision. They not always return the pointer, let the pointer point to different things. They return either the pointer or directly access to the buffer. Hence of that, the two-argument constructor looks slightly different. So we default initialize mbuff that our union has a defined member. Size gets updated to the length of the string, and capacity now has to check whether it fits into SSO. Then we set SSO capacity to capacity. Otherwise, we update that one to length. And in the constructor's body, now we have to query once again, does it fit into SSO? If so, we do nothing, but if not, we have to allocate dynamic memory. And of course, we have to copy the data as before. So two different implementations, they both yield 7 bytes of payload, right? Summing up to 24 bytes in total. Can you do better? I'm not sure about you. I'm sure about mine. I couldn't in the beginning. This is Clang's implementation. It's the newest among them, so let's say they could have learned a lot from the others. And you can tell if you're a quick reader on the slides, it's more complex because it doesn't fit on a slide anymore. If you look at the very bottom, I have to say, to be continued. So what Clang does is they say they have two structs, normal and SSO. And normal here starts with a size T single bit field called large, followed by a size T bit field capacity, which has the number of bits of a size T -1, because that's the one we just spent for large. Then there is another data member size, also of type size T, and a car pointer data. So that's the struct normal. And alongside that, they have a struct called SSO. SSO starts the same way. This time it's a uint8t called large. It's a bit field of a single bit. And followed by a uint8t called size. That's a bit field of your uint8t's bits -1, so typically 7. Followed by a couple of padding bytes to pad everything up, such that data here, my data array this time is nicely aligned. And data now contains or has the size of the struct normal -1 size T. So assuming 64-bit, size T, 8 bytes, 24 bytes we want in total, that means 16 bytes SSO buffer. -1 for the null terminator, that means this implementation gives you 15 bytes of payload. Awesome. It's twice the amount the others had. However, we might have to pay for that, right? So they pack everything in a union where they say either small or large is active, easy thing. And then we have the max capacity. That one now is reduced as the power of 2 of the bit capacity, so your size T is bits -1. We have SSO capacity, that's now, as I said, 15 bytes. It's quite good. SSO fits into SSO same as before. Islong reaches for packed.small.large, so the bit that indicates whether we are in large mode or not. And then we have default constructor small string, and in the two arguments, so we'll really get a string, we check, or we first create a small string, and then we check, does it fit into SSO? If so, we simply update the length in the SSO mode. Otherwise, we flip the bit and say we are in large mode and update the length in the large mode. Then we would copy the data over. Now here's the gotcha where your ping for is 15 bytes of payload. Sounds nice. But if you look at size, data capacity, all of them now come with a branch, because each of them has to figure out whether it's small string mode or not. So this is the downside of that. But you get 15 bytes of payload. Now you saw 3 implementations, and I know it's really mean to ask you that in the middle of a presentation where you're maybe sleeping, maybe not. Can you do better? Maybe let's think about what's the theoretical maximum that we can achieve. So we want 24 bytes in total, right? We have now seen this nice bit fiddling technique. I like that. We can say we need at least 1 byte to store the length, because in small string mode, where we can store less than 24 bytes, 24 bytes, we are sufficient with a uint AT. Signed or unsigned wouldn't make a difference, right? 8 bits are enough. We could spend another byte to store the information, whether we are in long string mode or not. That would leave us with 22 bytes, minus 1 for the null terminator. That means 21 bytes in payload we could achieve. But some of you are potentially in embedded, and if you're quick enough, you notice that 24 bytes or less, we don't need the full 8 bits my unsigned car would provide. So we could use 1 bit from that unsigned car to store the information whether we are in large mode or not. That would get me up to 22 bytes of payload. 1 for the length, 1 for the null terminator, so 24 minus 2, 22. Doing math at a Saturday morning might be mean, but I think you can watch it later and see that I'm right. So the theoretical maximum here is 22 bytes. Does anybody disagree and see a higher number? Terminating 0 can be used as an indicator. Very well. Anybody else? All right, instead of talking to me after the talk to Andreas. We can do better. At least one person could in the beginning, and that was Andrei Alexandrescu. The 4th implementation here is from Facebook. It's FB string. It looks a lot like libc++ that we just saw. It comes with 2 structs, normal and SSO. Normal stores a pointer, data, car, star, a size, and a capacity. And there's a note that the capacity is virtually reduced by 1 byte. So the most significant byte here is used for something else. SSO only contains a car array with the size of normal, so full-fledged 24 bytes. They pack that in a union like Clang did, sums up to 24 bytes. We have SSO capacity power of 2 with my capacity reduced by 1 byte. We have the SSO capacity, and that's interesting. They say SSO capacity is 24 minus 1, so 23 bytes payload. They have 2 or 1 member function here in const and non-const version, get mode byte. And there they fetch the most significant byte of the data array. Fits into SSO, same as before. Islong fetches that mode byte and checks whether this mode byte has the 7th bit set. Why the 7th? Because that implementation is real fancy. They know a short, a medium, and a long string. And the medium string sets the 8th bit. So this is why the 7th. But the remaining 6 you have beneath them, they're enough to store the capacity you can store in small string mode. So what they're now doing, default constructing a small string optimized std string, and in the version where we provide a string and the length, they check whether it fits into SSO. If so, they fetch the mode byte. Remember, the most significant byte in this 24-byte array. And instead of storing the actual size of the string currently, they say we subtract the size of the string from the SSO capacity. So that number goes down to 0. And 0 incidentally, is your null terminator. So they combine the information of the length in SSO mode and which mode we are and the null terminator in one single byte. You pay with the same things as for Clang. We have now branches in all the 3 access functions. So the next thing here, now we are departing from the standard library, it's Constexpr. And I do teach C++, right? So I also teach Constexpr. I do consult, so I hit Constexpr there. And I always approach people who tell me that Constexpr isn't that great, my example isn't that great, they don't get it, and it's just a waste. If you watched Hannah's keynote yesterday morning, she also has convincing arguments. Here's the best one I found. It comes from a consulting project a while back. The client contacted me. They were running out of RAM. And of course, it was short before the release, so they wanted some way to make that product shippable. And after some investigation, I found out that the small embedded device mainly was transmitting strings. So that was one of the main jobs there. So you can say the heart of that application was a data structure called fixed string. Something similar we have in, maybe we have in 26 in the standard. It takes a single non-type template parameter of size. That one is used to construct a car array mdata here inside that fixed string. That's why it's called fixed string. We store the lengths alongside, so how many characters are really in that string. It's default constructible. It has a constructor taking a const star. That one figures out the lengths and copies the data over. It has, for access purposes, a size and a data member function. That's just to give you some idea here. And now they started using that fixed string a long time ago, like you see it in line 24. So that said to their developers, here you have this fixed string class, make it work. And let's be honest, do we developers really enjoy counting characters in a string? We don't. So everybody has sat down and said, yeah, 50 bytes, that should be enough for that string, right? If you're kind, you say 48 because it's a nice number. Some said 128, you just want to be safe and you have to change that one. So they practically over-allocated a lot in my object X here. They understood that before I came in, so this is why they have this function make fixed string, which takes your car star array, keeps the arrayness, figures out the lengths, and allows you to create a perfectly trimmed fixed string object. And this is what's used in Y. If you look at the code, the object X and Y are already const, they are already static. So I saw that and I told them, well, why not make fixed string Constexpr? And the response I got is, it will not help. The objects are already const, they are already static. What will Constexpr do for me? Since I was on their budget, it was a fight to convince them that I need maybe 30 minutes to make that thing Constexpr, and let's have a look at the effects, right? So I finally succeeded. This is a comparison version now this time. We have on the left-hand side the code from the slide. There's a little more, so it prints out the string, but otherwise it's the same, except for this uppercase string that you can see here, Constexpr. You can guess it, it's a macro, right? And I use it to have one compiler set Constexpr to nothing, while the other one here sets this define to Constexpr as it should be. So my left compiler here uses the original code, while my right compiler uses the Constexpr code. And for starters, I start with 0. So the original version here takes 209 lines of assembly code in Compiler Explorer. There are a couple of blanks, let's not get hung up on them. My Constexpr version here takes, 78. I would say that's a lot less than the original version. So despite const and static, it's a lot less. But who runs 0, right? Nobody runs 0, so let's use 03. Oh, good. So O3, 42 bytes or 42 lines of assembly code, way better. So yeah, they were right, it's good. Still, my Constexpr version seems to be more efficient. 31 lines of assembly code, right? It's not that huge, on a first glance, at least. So there is a 10 assembly line difference. And I don't want you to be fully fluent in assembly. The 10-line difference, if you take the time after the talk, comes from the highlighted code here. And what that highlighted piece of code does is it's responsible for creating your static objects which have a constructor. So what that piece of code does depends on how good you are with x86 assembly is it basically creates stack space or allocates stack space, and then it copies the strings from your ROM to the RAM. So your string already allocates space in your ROM. Now you pay for that a second time in the RAM. If you want to waste things, perfect, do that. If not, maybe don't. You also pay with time for the copy operation. If you have time left, do that. You can squeeze it out in the next release, make your customers happy, but that might not be the best approach, right? So this is not there on the right-hand side. This is where the difference comes from. So my right-hand version does not consume stack space or RAM for the strings that are already in the ROM, and it does not make you spend time on the copy operations. It's even better. Have a look at the left-hand version here. They have this constant here, lstr. It's a C-style string, right? This is what my compiler understands from a fixed string in the Constexpr mode. It understands that we are talking about an object X, which has a first field with the value 22. These are the number of characters in that string, followed by padding because the developer overallocated, followed by another piece of padding because the fixed string cannot be sufficient for everything. This object X, if you look at the printf, we can see that the compiler can use it directly here. So it can access that X and that Y. While on the right-hand version, we always have to access the stack version here and play some additional tricks. So I might be wrong because predictions for the future are always hard, but let's say, at least for now, this is the best example I can give you why Constexpr really can change things for you. And it wasn't that hard, just adding Constexpr to everything. So there's one more thing I have. Std initializer list. This is the type that std uses when you initialize it with a bunch of values directly while constructing that vector. And I rip out the class part, so we focus on the std initializer list. Remember, it's a non-owning thing, so it's not a container. Its real purpose is for initialization, so you should not start using it like I'm doing here. But this is for simplification reasons. Let's say I have a std initializer list of type int, call that one list, fill it with a couple of numbers, and pass it to a function receive. If you never looked into a std initializer list, C++ Insights here, once again, can help you understand what's happening behind. If you turn on the optimization transform std initializer list and do the actual transformation, you can see behind the std initializer list is array, which is const. The size is equivalent to the number of elements that you pass to the std initializer list. The type is the std initializer list type. The values there get copy constructed into that array. Your std initializer list consists of a pointer to that array and the number of elements. So that's the real std initializer list. The compiler always plays the trick, so that's a very special data type in the standard std initializer list. So we have a backing array always on the stack, which we cannot control. Compiler does that for us. Now with that in mind, we have an array. So let's suppose I have a function receive that takes conceptually a const array of int of size 4. The note below here says, don't do that at home. My friend Patrice reminded me of that. I haven't used the std array to stay simple here, but while the signature suggests that it takes only an array of size 4, it's a lie. You can pass any array and any pointer to that thing. But I wanted to visualize conceptually, it takes the size of 4 integers here, an array. Now I put that list of size 4 on the stack in fun. I have my function receive called with that list. So that's roughly what a std initializer list does in the background, right? How good or bad is that? The code is bad. As I said, you should use a std array. But it's easier comparable in Compiler Explorer if we omit that. So this here is the code in Compiler Explorer for the example I just showed you. And if you look at the assembly, you can see a familiar pattern. It's the same that we had just with Constexpr. Compiler, of course, understands that 3, 4, 5, and 6 are constants, so can put that one in the ROM. We are allocating a bit of stack space. We are moving the data from the ROM to the RAM. And then we are passing that thing to the function receiver. Now we're seeing the same pattern here, but we have no way to access this array in the case of a std initializer list. Now the reason the compiler has to do this as you see it here is simply that the standard guarantees you that if receive would call fun recursively, that the const array list here has a unique address in each recursion step, because maybe you would fill it with different data. And then you want to have a fresh array. So this is why in this case the compiler must ensure that you get a unique address here. And with that a new array all the time. I didn't provide the compiler with the implementation of receiver. If it can see receiver and it can understand that it's not doing any recursion, it could do better here, but you cannot bet on that one. So we can improve this code here by saying we make this array static. If I do so, you can see the code is way shorter. And this is because in fun here, the compiler now is able to directly access the data from the ROM and pass that one. It does not have to create stack space and copy the data into that stack array. It can just use the data. So previous version, creating stack space, copying things. This version, not doing it. Okay? So, sounds good. Let's make that thing const and static, and we are done. But making your std initializer list static is not an option because you not use the std initializer list in the way I do. You create a std vector with a bunch of elements. You never create the std initializer list yourself. So there's nothing you can make static. And even if you make the std initializer list static, the backing array doesn't care. So what can you do? I'm not sure if it's the best thing you can do. It's not necessarily easy, but it might be worth it anyway. If we have that piece of code again, and look at this in Compiler Explorer, that's the bad version from the beginning, right? This time it's vital to look at which version I'm using of the compiler. That's GCC 13.3. I'm on C++ 17. This is GCC 14.2. Did you see the difference? It's the same version that I just showed you when I can make the backing array static. The compiler now in this version can access this array directly. There is a change in C++ 26. It's a defect report, so we can, or compiler writers can apply it retroactively. It's not bound or limited to 26. It goes backwards to any standard up to C++ 11. And that fixes if your compiler can prove that this std initializer list here contains only constants, so this is the usual way how we initialize a std vector very often, then it can make this backing array static. It does not have to account for the recursive case because this doesn't apply. So this is by upgrading your compiler how you can improve your code. And you can do a lot more nice things if you upgrade to GCC 14.2, you have C++ 23 and other things available. So it might be worth it, despite it might not always be the easiest thing to do. All right, so I hope you enjoyed that. I hope you learned something. I do training classes which focus only on efficiency, so this is just a small peek if you want. Can do more in 3 days. We have time for questions left, and before we do so, let me say I'm Fertig. Thank you.
Sorry. Thank you very much. We have one question from the online audience, and Markus Werder is asking, on the libcpp slide, you used packaged small large without knowing what type the union holds. Isn't that UB?
So if I got that one correctly, very observant, by the way, so congrats on that one. I guess we are talking about this slide here, right? Where later then I say that I access always packet.large.size, or more precisely the question whether it's large mode or not. And UB is a very good point here. Of course, it's in the standard library, so it's not UB. You can look at class.mem.general, paragraph 28, speaking in standard terms. The longer answer might not be better, but there is a thing called a common initializer sequence, which is a very long thing to describe, so I'm not trying to do, but in the end, it means that this specific use here is not UB. Yeah, but very well spotted.
Thank you. It's okay. So firstly, thank you for your talk. I have a question about porting these changes to creating a vector with a small buffer optimization. So having some elements on the stack and then moving to the heap. How many of these principles can you think they may apply for constructing a vector with a type T?
So for the vector, there is no small string implementation.
So a vector with small buffer optimization.
Yeah, a vector does not have a small buffer optimization, if I'm correctly, because of the iterators,
Okay.
To keep them stable. Clang, in their internal implementation, they have something like a small vector, small array, that they have stack space behind it. But this is a optimization technique only for std string.
Okay, thank you.
You're welcome.
Hi. Thanks for the great talk. My question was same as the first one. Out of those 4 implementations for SSO, 3 of them use the member of the union that you don't know if it's active or not. And I didn't quite get the explanation. Maybe you could repeat.
So I just let me try it like this. This is not necessarily the question, the answer now for you right now, but this is the answer you can try to look up later, okay? Because I don't have a better reference. So you find it in the standard under class mem general paragraph 28. So and what you find there, so this is for the recording primarily, what you find there is that the standard talks about a common initializer sequence. And that roughly says if you have, let's simplify it totally, if you have a union with two char arrays as members, because in bits and bytes they are the same, they have a common initializer sequence. If you access the one, it's not UB. If you access the other one, that's not active. So this is a very, very special case.
In the first example, there's capacity and a char buffer. Does that include that as well?
In the libc++ version here, this one,
S3 C++, I think.
libstd++ doesn't do that. They don't fiddle with bit fields, so they are totally safe because they know that they either have capacity or mbuf active. It's only libc++.
But in islong, you're accessing mbuf, which might not be the active member.
Yeah, that that falls under the same rule. They have a common initializer sequence. Sorry, the term is very unknown. It's very complicated. It takes a whole section in the standard. But it's a very special case. I'm not really advising you to do it because it's obviously difficult to understand when and when not it's UB. But that one here is authorized by the standard.
On a side note, what's your recommendation for something like this? I'm assuming all the practical compilers would do the right thing and not give you a real UB or some unexpected side effects. So what's your recommendation for things like this? Should you stick to the standard as much as possible, or you can?
So that's a very tough question because your standard library technically can do something else. The standard library is supposed to ship with a certain compiler, right? And they can know that in their compiler, this is not UB. So by that, they could do things specific to that environment that are not allowed by C++ technically in general. So sometimes it could be difficult looking at a standard library and seeing what they are doing. I would say if you really have to optimize like that, you have to learn the things. And otherwise, I would try to stay away from them.
Okay, thank you.
You're welcome.
Hi. In the fixed string example, it seems like the advantages from const expression were mainly because we are talking about literals here and not because of anything else, right? So if I would use the fixed string, for example, to have a contiguous memory of, say, like those 50 bytes or 50 characters are always, like in a stride, that would be an advantage for dynamic strings as well in certain cases. But the advantages you showed in Compiler Explorer, they were mostly because they were literals, so they could be put in the static section, right?
Because Constexpr made them real literals, if this is what you're saying.
What I'm saying is I can use fixed string also for dynamic strings and not just for literals. And then the advantages would be much less, wouldn't they be?
By dynamic strings, you're meaning something that you put in at runtime. Yes. In that, yeah, sure, because then it's no longer the constant. So this was only the constant.
So they littered basically their entire code. All right, okay, thank you.
You could use Constexpr to create a concat some strings at compile time, right, and make that one a literal, store it in there. This is something, but otherwise, totally right, yeah.
Hello. In both examples of the small string optimization, you mentioned the cost of the branch in the size 2 functions where you query something in there. How much branch prediction can help you with that, and how much is that really a cost? Because the branch, you always take the same branch for a particular string, right?
That's a tough question. I mean, for the particular string, yes, whatever particular means to your branch predictor. Because if you would go back to small string optimization, things would change. If you exceed small string optimizations, the branch is different. So I don't know. I don't know.
Okay, thank you.
You're welcome. All right, we are out of time. Thank you very much. If you have more questions, approach me in the hallway.